I've got our first problem up here where we're going to use the extreme value theorem for functions of more than one variable. In particular, we've got a function of two variables. F of xy is xy minus x squared minus y. And I've just drawn a picture of the region D that we're working on. Okay? So we're not working on the natural domain of f. We're restricting f to this region D, which is the region that lies above the parabola y equals x squared and below the line y equals 9. And you'll notice I drew in both parts of the boundary curve as solid curves. That's to indicate that that boundary is included. So everything that's on or above the parabola, everything that's on and below the line. Okay, so we're first asked to verify that f has an absolute max and an absolute min on D. Well, the theorem that will tell us that is the extreme value theorem, so I just have to make sure that we've satisfied our conditions. So I need f to be continuous on D. Well, f is a polynomial in x and y. It's continuous everywhere. So that's satisfied. Okay. Then there are two criteria for D. It has to be closed. Well, I just stated that we were including the boundary. And it has to be bounded. It doesn't go off to infinity in any direction. So it was important that I put this cap on the parabola. I couldn't just say everything above the parabola because that would have gone off to infinity. So it is closed and bounded, so the extreme value theorem applies. By the extreme value theorem, f has an absolute max and an absolute min. I will hold you responsible for being able to state the extreme value theorem. Okay, it's pretty simple criteria. Make sure you know what they are. Okay. All right, now the second part of the question, we're asked to find the location and value of the absolute max and min. I will almost always phrase my questions this way. It's a two-part question. I want the location and I want the value. And make sure you make it clear in your answer which part of your answer is the location and which part of your answer is the value. All right, now I know that the absolute max and min can only occur at certain types of points. So I'm going to create a table of values. I'm hoping to list every possible location for the max and the min. And then when I plug into the function, whatever I get as the biggest value, that's the max, and whatever I get as the smallest value, that's the min. The types of locations we could have are critical points and points on the boundary. Okay, so let's go ahead and look at critical points first. So I'm going to take a look at the gradient. So the gradient of f, partial of f with respect to x, comma, partial of f with respect to y. Let's see, partial with respect to x, that's going to be y minus 2x minus 0. Partial with respect to y, that's going to be x minus 0 minus 1. Okay, now that gradient is always defined. Okay, so I won't have any critical points from it not being defined. The gradient of f would equal 0 if both components are 0. So y minus 2x equals 0 and x minus 1 equals 0. Now that second equation tells me that x would have to equal 1. Plugging that in here, y minus 2 would have to equal 0. Y would have to equal 2. So we're looking at the point 1, 2. Now, is that point in D? Yes, because if we're at 1, the point on the parabola would be 1, 1. So 1, 2 is going to be above that, and that's definitely below 9. But it is always necessary to check. There are probably going to be some times when you find a critical point, but it's outside of your region D. Don't include it on the list. This one's in our region D, so I will list 1, 2 there. Okay, let's go ahead and evaluate our function there. So x times y would be 2, minus 1 is 1, minus 2 is negative 1. Okay, now the boundary. The boundary actually comes in two parts. Very important that we recognize that. There's boundary part 1, which is the parabola, and boundary part 2, which is this line. And I'm going to need to deal with each of those separately. Now, each of those contains infinitely many points, so I can't just list all of those points here. But what I can do is I can parametrize the boundary. So I'm going to let R1 of t be parametrizing the parabola. Since y is a function of x, I can just let x be t, and then y becomes t squared. That would parametrize the whole thing. I just want this portion of it. And I can see this point would be the point -3,9, and this point would be the point 3,9. So basically, I want t to vary from -3 to 3. So I've parametrized that curve. Now what I'm going to do is look at f applied to R1 of t. I'm going to look at the curve I get in 3 space if I plug points on that boundary curve into my function f. So x times y becomes t times t squared, or t cubed, minus x squared becomes minus t squared, minus y becomes a minus t squared, and again, I'm looking at this on the interval from -3 to 3. I can combine some terms here, so that's t cubed minus 2t squared on the interval from -3 to 3. Now notice, when I apply f just to the boundary curve, if I've parametrized that curve, I'm actually getting a function of one variable. This function is continuous. We are working on a finite closed interval. So the extreme value theorem for functions of one variable applies to this function here. That's how I'm going to narrow it down from the infinitely many points that occur on the boundary to just the important ones, which are going to be the critical points and the endpoints. I'm actually going to create a separate table of values just for this boundary curve, and that's because I've got some more information for this curve. I'm going to have a t value, and then an xy value, and then an f of xy value. And here, I know that I want to check critical points and endpoints. Now my endpoints will be -3 and 3. And of course that corresponds to these points here, -3,9 and +3,9. For critical points, I'm going to need to take the derivative of this. Do be careful with your notation. There is no such function as f prime, because f is a function of 2 variables. So I'm going to take the derivative with respect to t of f of R1 of t. That's going to be 3t squared minus 4t. That is always defined. When is that 0? 3t squared minus 4t equals 0. Well, I can factor. So that's t times 3t minus 4 equaling 0. So t would equal 0, or t would equal 4/3. So I've got 2 critical points, t being 0, t being 4/3. If t is 0, my point xy is 0, 0. I should point out both of these numbers are between -3 and 3. So they both will correspond to points on this boundary curve. If t is 4/3, my point xy is 4/3, 16/9, because we're on the curve y equals x squared. So let's go ahead and evaluate f here. I know from the extreme value theorem for functions of one variable that there's guaranteed to be an absolute max and an absolute min just on boundary curve 1, and I'm going to transfer those points onto my master table here, which is applying to the entire region D. Okay, so if I plug in 0, 0, I'm going to get 0. Okay. If I plug in 4/3, 16/9, let's see, x times y, that's 4/3 times 16/9, minus x squared is going to be 16/9, minus y is going to be 16/9. I'm going to just factor out the 16/9. That's 16/9 times 4/3 minus 1 minus 1. Okay. So that's 16/9 times, let's see, that would be minus 6/3 times a negative 2/3. So I'm going to get negative 32/27. Okay. Let's take a look at negative 3/9. Okay. So x times y would be negative 27. Minus x squared is minus 9. Minus y is minus another 9. So that's going to be negative 45. Yes, negative 45. All right, and if I plug in positive 3/9, x times y is 27, minus x squared is 9, minus y is 9. That's 27 minus 18, that's 9. All right, so if I take a look just on the boundary curve here, I can see that negative 45 would be my min for just that portion of the curve, and 9 would be my max for just that portion of the curve. Which means these points don't even qualify as being the biggest or the smallest just on the boundary curve, so they can't possibly be the location of the absolute max and the absolute min on D as a whole, but these points could. So I'm going to translate these to my master table. So we'll have negative 3/9 and 3/9, and our values were negative 45 and 9. So just looking at things, so far, it does look like that's the lowest value we have, and that's the biggest value we have. But we haven't checked the entire boundary, because the boundary came in two parts. We've also got that horizontal line. So I'm going to call that R2 of t. Now there, my y value is just fixed at 9, so I can let x just be t. And once again, it looks like t is going to vary from negative 3 to 3. Okay. Now that's just parametrizing my curve. Remember, we're trying to maximize f, so I need to now plug that into f. So f of R2 of t is going to be x times y becomes 9t, minus x squared becomes minus t squared, and then minus y becomes minus 9. Okay. All right, notice this is a continuous function of one variable defined on a finite closed interval. So I can apply the extreme value theorem for functions of one variable. I'm going to take the derivative of f of R2 of t, and I'm going to get 9 minus 2t. That is always defined. When is it 0? If 9 minus 2t is 0, that would mean that 9 was equal to 2t. T would equal 9/2. Ooh, that's not in the interval. So something we need to be very careful of. We're generally, with these problems, not working on the natural domain of our functions. This function would be defined for all values of t, but I'm only looking at it between negative 3 and 3. 4/2 is not in that interval, so there are no critical points in that interval. Now, I'm still going to create a table of values for just R2 of t. Let me do that over here. Again, I'm going to have a t, an x, and a y, and an f of xy. There are no critical points. So I'll just indicate there weren't any in the interval, but I do need to check my endpoints. So negative 3 and 3. That's going to correspond to the points negative 3/9 and positive 3/9. And one thing that's nice is the endpoints for this section of the boundary coincide with the endpoints for the other section of the boundary. So we've already plugged in. I know at negative 3, 9, I get negative 45, and at positive 3, 9, I get 9. So I don't have to do that work again. Okay. These points, I want to make sure they're on my master list. They're already there, so I don't need to write them again. Okay. However, if I hadn't checked boundary curve 2, even though it didn't give me any new points, I didn't know that until I checked. So it's necessary that you check critical points for the overall function, that's critical points in 2 space, and then all sections of the boundary. And when you do that, notice you're going to have your parametrization, f of your parametrization to get the curve you get by applying the function to that boundary curve, and then the derivative. If you don't have all 3 of these things, you've done something wrong. Okay? A lot of times I see people try to work with just this, they forget to take the derivative. Or sometimes they're even working just with the curve, forgetting that that has nothing to do with f until I actually plug it into f. Okay, so it turns out we only had 3 possible locations for our absolute max and our min. Now I can see that that's my min and that's my max. They both happen to occur on the parabola part of the boundary. Now, simply labeling things like this is not answering the question that I asked, because I asked for the location and the value. That doesn't make this clear. So I would write out f has an absolute min of negative 45. That is the value of the min. It occurs at negative 3, 9. That is the location. F has an absolute max of 9. That is the value of the max. It occurs at 3, 9. That is the location of the max. Okay. So I wanted max and min, and each of those had 2 parts, location and value.